Thanks for the introduction. So with the introduction of immersive virtual environments that utilize head-mount displays and tracking technology, it has become possible to use natural walking as a means of traversing a virtual environment. Navigating through walking is ideal because it allows people to feel the correct proprioceptive and vestibular senses associated with walking. However, we run into an issue when we try to explore tracking areas that are larger than, virtual worlds that are larger than the available tracking space. So the question is, how do we allow users to navigate through these virtual worlds? And one method to doing this is with redirected walking. And what redirected walking does is it distorts the correspondence between the physical and virtual motion in order to steer users away from boundaries and obstacles in the room. And so, for example, you could have a user walking down a straight path in the virtual world, and you could rotate their viewpoint so that the user has to walk in an arc in the tracking area in order to stay on that path. And if the tracking area is large enough, then the user can walk in a circle in the tracking area while walking indefinitely in a straight line in the virtual world. Now, steer to center, the algorithm that's commonly used to implement redirected walking requires a large space to work effectively. So we want to try to find, we want to try to minimize the amount of space that the redirected walking uses, or to be able to support additional users. So I'll go over some previous work in multi-user redirected walking. Asmanian, Gretchen, and Rosenberg in 2017 looked at 3 different ways for implementing 2-user redirected walking. One was with a subdivision strategy, where each user has its own separate space. Another is where the user shares the space but uses either common center or offset center. And depending on the virtual environment you use, either common center works better, for example, in square tracking areas, while for rectangular tracking areas, offset center works best. So now I get into artificial potential field. So this was presented in the last talk, so I'll just go through it briefly. The idea is that each obstacle in the room, including other users and tracking area boundaries, exert a force on the user. And this force is dependent on the distance between the obstacle and the user. So closer obstacles introduce a larger force. And the idea is you sum these forces, and that gives you the net force. And the user is steered towards that net force vector. And the advantage of this approach is it's very simple to calculate, and it's the target the user is steered towards is dynamic. So now I get into the modifications done in this paper. So we want to be able to support multiple. We want to be able to support irregular convex spaces, and we do this through several new improvements. So originally we didn't take into account boundary size when calculating the force. So now we have it so that smaller objects produce less force than larger objects. Boundaries that face away from the user are no longer calculated, and we also scale the force based on the size of the, and we also subdivide boundaries into smaller segments so that defining the boundaries doesn't influence the force calculated. We also introduced the idea of proximity scaling. This is used if a user is guaranteed to hit an obstacle with their current speed and heading. In this case, if we apply the maximum amount of redirection possible, we will still have to trigger a reset. And this is not ideal because the user has to interrupt the task that they're performing. So one idea is to try to temporarily increase the redirection rate in order to prevent this reset from occurring. Of course, there's a trade-off. As we're steering users past the imperceptible rate, they might notice the redirection, but we should be able to quantify this redirection, quantify this effect. So now again to our method for testing artificial potential field, and this is done through simulations, but these simulations are based on live user data collected from 4 previous live user experiments. These range in a multitude of different environments, including open spaces and enclosed closed spaces such as a grocery store, and it also utilizes several different, each experiment uses different tasks. So we have, so using these paths, we demonstrate typical user walking patterns, and this is preferable to using computer-generated paths. So in one test, we test redirected walking algorithms in square rooms of different sizes, ranging from 10 by 10 all the way to 50 by 50 meters. So for each square room, we look at single user, and we also extend this to multi-user. So we'll run 2-user trial, 3-user trial, and so on. And we arbitrarily place users on a diagonal with fixed spacing, so that there's a maximum number of users that we can start in the tracking area. And for each of these tests, we use all 288 logs. And in the case of multi-user, we use 500 user trials. We also tested the algorithm in different shaped rooms. So, and this, and so for example, we look at both open spaces and then also concave rooms to see how the algorithm performs. And all these shapes are scaled to have a 1,000 square meter area. And we're testing 4 different conditions. So we're testing control, so no redirection is applied whatsoever. Steer to center, where users are steered towards the center of the room. Artificial potential field without scaling. So comparing between artificial potential without the proximity scaling allows us to see how direction influences the number of interruptions. And we're also testing artificial potential field with scaling, so we can compare it to the version without scaling to see how much of an impact proximity scaling has. And in all methods, artificial potential field resetting is used. Even in the cases of control and steer to center, this is based on the gradient of where the user implies a reset. So first, let's look at the maximum number of users you can support in square rooms. And as an arbitrary cutoff, we say that this is 1 reset per minute. So with artificial potential field proximity scaling, you need at least a 20 by 20 meter tracking area to get under 1 reset per minute. However, slightly increasing the size of the tracking area space allows you to support more and more users. And by the time you get to a fairly large tracking area, but a 40 by 40 or 50 by 50 tracking area, you can support well over 10 users. And in fact, you can support the maximum number of users that that tracking area could support if you place users on the diagonal. So this is looking at the distance in between resets as you increase the number of users. And as you can see for steer to center, the distance in between resets drops off quite quickly. And because users are being steered into each other, this triggers more resets. However, for artificial potential field, it takes much longer for this fall off to occur, and therefore it can support many more users. In addition, artificial potential field allows users to travel farther. However, it only slightly affects the average steering rate. So now we'll look at how artificial potential field works in different room shapes. So for this graph, the blue shows artificial potential field, and so the blue line shows artificial potential field, the orange line shows steer to center. And the thing to note about these plots is that artificial potential field attempts to use the entire space of the tracking area, while steer to center only tries to fit a circular region in the central part of the room. So now we're looking at the average mean reset across the different room shapes for all 4 different algorithms. And as we can see, artificial potential field performs much better than steer to center, particularly in the case where you add proximity scaling. And so in conclusion, artificial potential field outperforms steer to center in the number of users that it can support. It also artificial potential field outperforms steer to center in handling irregular concave rooms. And finally, artificial potential field has clear advantages over the unscaled version while having a relatively small effect on the overall redirection rate. So any questions?
So, if I understood correctly, the problem with the proximity scaling is that you can curve too much and then you'll notice that you're being redirected, right?
Yes.
Okay, so did you guys measure that?
So the proximity scaling can potentially go above perceptible threshold rates in the study. One thing we didn't look at into, since this isn't a live user study, does this actually influence how much you can, would users actually notice this increase in redirection? And also, if they do notice it, would it be preferable to perform a reset where the user has to stop what they're doing and perform that reset, which can take valuable time away from the task they're trying to complete. Does that answer your question? Or we could potentially talk afterwards if that's preferable.
All right, great talk, thank you. So we now have a new way of evaluating redirected walking algorithms, which is this kind of hybrid of simulation but using live user data. So obviously, actual live user data is the best way to
Yes.
do this, but not everyone has a Hive lab, and it's very difficult to run the number of people required, right?
Yes.
So I was just wondering, like, what are your thoughts on the pros and cons of using this hybrid approach to using a computer-generated approach?
Well, the pros is obviously you get typical user walking patterns. You get the direction users were facing. You also introduce the noise, like the actual noise that you'd get in the tracking area. So you see exactly what the redirected walking algorithm would see in the virtual environment. The disadvantage of this approach is that, for example, if you increase the amount of redirection you apply, the question is, these type of studies isn't going to replace actual threshold-based studies.
Right.
And whether users actually prefer like one technique over another, for example. Does that answer your question?
Yeah, I think so. Thank you.
So I had a question, but Gerald still does, so thank you. So I'll ask another one. It's sort of related to the last question. So this was a really fascinating use of live user data that was previously collected. And to my knowledge, you're the first people who've done it, so it's really, really interesting. And I'm wondering if, can we use that, do you think that there's a value in using sort of like that live user data to maybe make a better simulation model that more mirrors kind of these natural walking paths? Or does your intuition tell you that actually like just the typical way of just using the simulation without sort of like even a natural walking path, do you think it is ultimately going to change the significance values of like the redirected algorithm performance metrics? Or do you, like what benefit really is there over so many long distance walks of kind of like the natural kind of walking paths?
That's a very good question. if you have time afterwards, I could definitely talk to that with you.
I don't know the answer.
Yeah. I definitely have to think about it.
I'd say the biggest thing if I do is that simulated users never like look around while they're wandering, and you can inject a lot of extra redirected walking during and without looking on the path. So you actually end up with more redirection for live user data than just synthetic.
All right, let's thank our speaker.